Welcome to this lecture on computing with joint PMFs of two random variables. Okay, so you must have seen Prosarvan's lectures on how to do computation of marginal PMF from the joint PMF and how to do computations for probabilities of different events involving two random variables. Okay, so these two are extremely crucial ideas. Once again, in this lecture, I'm going to take some simple examples and illustrate how to do these calculations. So let's begin. So this is a computation with the joint PMF. Okay, so the first example I'll take is some sort of an artificial example where I give you the PMF and then I ask you to compute some basic things. So that's also very important to see. Let's take a joint PMF. Once again, I'm going to have this notation for the joint PMF where I put a table and then I put probabilities corresponding to the table. Okay, so I'll take a very simple case where x takes 2 possibilities and y takes 3 possibilities, and I will then put probabilities here. Now remember, I have to put probabilities so that they all add up to 1. Okay, and I will do it in a certain way. I mean, one can do multiple things here. Nothing is really critical here. So let's say I put 0.1 here, 0.3 here, 0.05 here, 0.4 here. I'm just making it up as I go. So maybe 0 here, and then I have to put here something to make it a valid PMF. Okay, so I put some values here for x and for the joint PMF of x and y. I've put 1, 1 as 0.1, 2, 1 as 0.3, 1, 2 as 0.05, 2, 2 as 0.4, 1, 3 as 3 as 0. What should be 2, 3? In fact, I can find out what should be this guy. Why is that? Because all of these guys should add up to 1. Okay, what are they adding up to? 0.7, 0.8, 0.85. So this should add up to, this should be 0.15. Okay, so this makes it a valid PMF. Okay, so this is one check. Like I mentioned, you have to always run, particularly when you calculate complicated joint PMFs, you should ensure that they add up to 1. That's a valid condition. Okay, all right. So now let's do computations now. The first computation that you should, it's important to understand, is marginal PMF. Okay, so this, like I mentioned, is the joint PMF of x and y. Okay, this is the notation that I have for it. Now the marginal PMF of x, okay, has only one entry here. X is 1, 2. Okay, so basically this tells you what is the probability that x is x, right? This is simply summation over all y probability that x equals x comma y equals y, and that is simply the probability joint PMF of x comma y. Okay, so for every x, what should I do? For every x, suppose I want to find the probability that x equals 1, I have to add the joint PMF over all y. Okay, so I should simply add up all the entries in the column here. I will get the probability. So this will just be 0.15 and this will be 0.85. Okay, so how did I get it? 0.15 is 0.1 plus 0.05 plus 0. 0.85 is 0.3 plus 0.4 plus 0.15. Okay, what about the joint PMF, the marginal PMF of y? Okay, so here once again, if you do this calculation carefully, I have to add up the values in every row, right? So if I can repeat the same thing, you will get the final formula as pxy of x comma y. You add up over all values of x, keeping y as the same. So y is 1, so I have to add up 0.1 and 0.3. I would get 0.4 here, 0.45, 0.15. Okay, so this, like I said, is 0.1 plus 0.3. This is 0.05 plus 0.4. This is 0 plus 0.15. Okay, so this is a way to calculate marginal PMF from the joint PMF. Simply add over the columns or the rows. Okay, so in this simple example, it works out quite nicely. In more complicated examples, like say the trinomial example that Prosarvan did for you in the lectures, you have to do more sophisticated computation, but essentially the idea is the same. Okay, so you add up over one of the variables to get the marginal PMF. Okay, so that's important to understand. Okay, so the next interesting calculations that Prosarvan does is he asks questions of events based on this joint PMF. then asks for probabilities of them. So let's do a few events. Okay, so the first event I want to do is x equals y. Okay, so what is the probability of x equals y? Okay, so suppose somebody asks you the question, what is the probability of the event x equals y? Okay, so here, so the first thing to do when you're given a problem like this in multiple random variables or one random variable is to first describe the event very nicely. So in this simple situation, one can describe the event as the set of possibilities that x and y can have. Okay, x can take two values 1, 2, y can take two values 1, 2. So if x has to be equal to y, x comma y should either be 1 comma 1 or 2 comma 2. Okay, so it's easy to list out this possibility here. So let me do maybe a blue calculation here to show where the event would be. X equals y is this event, right? Right, so this is the event 1 comma 1, 2 comma 2. X and y are equal. X and y could be both 1 or x and y could be both 2. Okay, so the probability of this is simply pxy of 1 comma 1 plus pxy of 2 comma 2. So you have to simply add those two guys. It's 0.1 plus 0.4, that's 0.5. Okay, so that's how you do events. Now you can do any other event of this form. There's nothing sacred about x equals y. For instance, you might want to do probability of x greater than y. Okay, so maybe I'll use a different color here. I'll use a green color for this event. So x needs to be greater than y. If you look at this possibility, the only way in which x can be greater than y is this guy. Okay, there's only one possibility by which x can be greater than y. Okay, so once again, if you want to write that down, x greater than y, the only possibility is x equals 2 and y equals 1. And so probability of x greater than y is simply pxy of 2 comma 1, it's just 0.3. It's a very simple example. And you can also do maybe one more example. Maybe I'll do that on this side. Probability of, let's say, y greater than x, just to make it a little bit more interesting. So maybe I'll use a violet color for this. And if I do that, if I'm going to skip a few steps, do it a bit quickly. So if I want y to be greater than x, the possibilities are these three, right? And the probability of that is simply going to be 0.05 plus 0 plus 0.15, that's 0.2. Okay, so this is how you do simple events in this easy case. If of course the case, the situation becomes more complicated, you have to do more sophisticated calculations. Like for instance, in the trinomial case, the calculations are not so simple, but nevertheless, the idea is, the concept is exactly the same. Okay, so let's also do a few more examples. The next example is conditioning, right? So conditioning is another thing that Professor Arvind talks about. Suppose I want a condition. So you condition on x equals x, right? So this is something that Professor Arvind talks about. So if you look at this joint PMF, I could condition on x equals 1 or x equals 2. Condition on x equals 1, so I will have a conditional PMF of y conditioned on x equals 1. Okay, so y conditioned on x equals x. Okay, so this is y conditioned on, let me just do this, 1, x equals. So if you want to do this this sort of PMF, okay, so if you condition on x equals 1, and then you do a PMF, so this is the conditional PMF. This would be pyx of pxy, I'm sorry, of x comma y divided by px of x, right? So this is the formula here. So since x is 1, so this is just pxy of 1 comma y divided by px of 1. Okay, so we've calculated most of these things here. Px of 1 is simply 0.15 and pxy will work out as 0.1 and 0.05. Okay, so if you do that, we'll simply get py given x equals 1 of y be the ratio of these two guys. For different values of y, this will work out differently. So it's good to write down like before. You put a y here, 1, 2, 3, and then I want py given x equals 1 of y. Okay, so this is going to be 0.1 by 0.15, 0.05 by 0.15, 0 by 0.15. So this will be 2 by 3, 1 by 3, and 0. Okay, so that's the conditional PMF of y given x equals 1. Is that okay? So basically the idea is you look at a particular column, okay, that will be the same proportion as the conditional PMF, except that you have to normalize it to 1. So you divide by the sum of all the values in that column. Okay, so 0.1 by 0.15, 0.05 by 0.15, 0 by 0.15. So you get that. Okay, the same thing on this side. This is going to be a little bit more messy in calculation, but it's the same thing. So you have to divide 0.3 by 0.85 to get the conditional PMF of y equals 2. So let me do that also here. So if you do y given x equals 2 of y, 1, 2, 3, you're going to have 0.3 by 0.85, 0.4 by 0.85, 0.15 by 0.85. Okay, if you want, you can simplify, you can divide by 5, etc. So you would get 6 by 17, 8 by 17, 3 by 17. Okay, so that's the conditional PMF of y given x equals 2. Okay, so these conditional PMFs differ based on what you condition on, and the idea is to simply take the particular column and then divide by the sum of all these columns. Now I can also condition x on y. Okay, so let me do that also. If you look at, so this is again y conditioned on x equals 2. Okay, so I might want to look at x conditioned on y equals 1. Okay, so if I do that, x is 1, 2, so I've conditioned on y equals 1. So this is just this row. I should take 0.1 divided by 0.4, 0.3 divided by 0.4. Okay, so it's 1 by 4, 3 by 4. Okay, you can also do x conditioned on y 2. So this would be 1, 2. If you condition on y equals 2, I'm going to get 0.05 by 0.45, 0.4 by 0.45. That's 1 by 9 and 8 by 9. Okay. In the last case, I might condition x on y equals 3. In this case, actually, you get a very, very simple answer. If I condition on y equals 3, it's 0 and 0.15. So it's 0 divided by 0.15, 0.15 divided by 0.15. So in fact, actually, I get a trivial random variable, which is 0, 1. Okay, probability that x equals 2 given y equals 3 is simply 1. Okay, there's no other possibility given y equals 3. Okay, so hopefully this simple example showed you the various types of computations that one does with joint PMF. And these are all very important to understand in a simple conceptual way. Okay, the first type of computation with joint PMF is computing the marginal PMF. Second type of computation is computing probabilities of events involving two random variables, which is greater, which is equal, or maybe even more complicated events. Maybe we'll see examples later on. And the third one is computing conditional PMFs given one of the random variables takes a particular value. So these kind of calculations are bread and butter. They're very, very important to understand, at least in simple cases like this. Okay. So I'm going to go ahead and give some examples from some sample spaces that we have considered in the past, of something very similar, and ask you to let's see the calculations of similar calculations, like what is the possibility of one thing being greater, lesser, etc. Okay, second example I'm going to see. So let's say we toss a coin 5 times. And so this is an interesting sort of situation, but one needs to be a little careful here. So now I have to start defining multiple random variables. Each toss can give me a head or a tail, okay? And I'm going to define the random variables in the following fashion. I'm going to say x is number of heads in first two tosses, okay? And y is number of heads in last three tosses. Okay, so we have 5 tosses: toss 1, toss 2, toss 3, toss 4, toss 5. X is the number of heads in the first 2 tosses, toss 1 and toss 2. Okay, okay, and y is the number of heads in the last 3 tosses. So this would be tosses: toss 3, toss 4, toss 5. Okay, so that's the 2 random variables, x and y. Once again, think about what these things are, and I have to. So let's start by doing the PMF like we did before, the joint PMF. Okay, so x is the number of heads in the first 2 tosses. It could be 0 or 1 or 2. Y is the number of heads in the last 3 tosses. It could be 0 or 1, 2 or 3. Okay. Okay. All right. So what is the probability that I get 0, 0? Okay. So I should have 0 heads in the first 2 tosses. Remember, the first 2 tosses, what happens in the first 2 tosses is independent of what happens in the last 3 tosses. They're not the same. There's no overlap. Okay. So when there's no overlap like this, it's easy to compute probabilities, because I can multiply the events independently. Probability of x and probability of y can be multiplied, because this what happens is independent of this. So that's something that I can use. Okay, so what is the probability that I have 0 here? It's 1 by 4. Okay, 0 heads in 2 tosses and 0 heads in 3 tosses. It's again 1 by 8. Is that okay? And then what is the probability of getting 1 toss, 1 heads in the first 2? That is actually 2 by 4, and then 0 tosses. This would again be 1 by 4 times 1 by 8. Okay, think about it. And then I would have the same 1 by 4 multiplying here, 2 by 4 multiplying here, 1 by 4 multiplying here, because the probability of x is the same. Probability of y becomes 1. Out of 3 tosses, I get 1. That's actually 3 by 8, right? So 3 by 8, 3 by 8. So likewise here I would get 1 by 4 times 3 by 8, 2 by 4 times 3 by 8, 1 by 4 times 3 by 8. Here I would get 1 by 4 times 1 by 8, 2 by 4 times 1 by 8, 1 by 4 times 1 by 8. Okay, so this is the joint PMF. Think about how I got this once again. So for instance, this probability, I'll just show you how I got this. Probability that x equals 1, y equals 2. This is probability of x equals 1 times probability that y equals 2, because what happens in x is independent of what happens in y. This is intersection, so I can multiply these two things. And this is 1 toss, 1 heads in 2 tosses. It's 2 out of 4 possibilities. 2 heads in 3 tosses, that is 3 out of 8. Okay, so this is just binomial calculations, or in other ways. So this is the idea. Okay, so this is your joint PMF. It's a little bit more, slightly more complicated, but you'll see some simplifications will happen here. Okay, so supposing from here I want to do marginal, I have to just add up everything, right? So suppose I want to do marginal here, marginal PMF, x is 0, 1, 2. I have to add along the columns. If I add along the columns, I see that this 1 by 4 is common, and if I pull this 1 by 4 out, I get 1 by 8 plus 3 by 8 plus 3 by 8 plus 1 by 8. That's just 1. So I'll have here 1 by 4, 2 by 4, 1 by 4. It's easy to do this calculation. And if you do marginals for y, likewise you will have 0, 1, 2, 3, and you can add up along the rows to get the marginals. You will get 1 by 8, 3 by 8, 3 by 8, 1 by 8. It's easy enough to do that. Okay. That's interesting. So now let's do other calculations. You can do more interesting calculations. So for instance, you can do, let me just keep this here and do calculations around it. I might want to calculate probability that x equals y. Okay. So you can see that's the event that you have along this diagonal, right? This diagonal here, x equals 0, y equals 0, x equals 1, y equals 1, x equals 2, y equals 2. This diagonal. So this will just be 1 by 4 times 1 by 8 plus 2 by 4 times 3 by 8 plus 1 by 4 times 3 by 8. Okay, one can simplify this calculation. This 6 plus 3 is 9, 9 by 8 fours are 32, 9 by 32. Is that okay? So that's the probability that x equals y. Probability that the number of heads in the first two tosses equals the number of heads in the last three tosses is 9 out of 32. And you might want to do more calculation. You might want to say probability that x is greater than y. This would be 2 by 4 into 1 by 8 plus 1 by 4 into 1 by 8 plus 1 by 4 into 3 by 8. Right? X is greater than 2. X is greater than y is this part. Right? The right top side. Maybe I should show that here. This is this calculation. And that works out as 5 by 5 by 32. So likewise you can do other events. So in fact you can do more sophisticated sort of events. I might want to define something slightly more tricky. So for instance I might say I need 2 more heads. So for instance you might say probability that y is equal to x plus 2. Okay, I might want to say that. So this will correspond to these two guys, right? Right? So you just mark out that event and add. Okay, so you get 5 by 32. Okay, so likewise you can define any other relationship you want between x and y. Y is less than x plus 2, y is greater than x plus 2, or any other way of demarcating this area that you want to have. You can write and you can compute probability. It's the way in which this probability is being done. Okay, you can also do conditional probability exactly like I described before. And in this case, you'll see this interesting thing that the conditional probability, conditional PMF, is the same as the unconditional marginals. Okay, so that comes from the independence as well. Okay, so this was a slightly more interesting example that comes from our examples. Okay, so you can also do similar examples. So I think I'll just finish with one more example. This is the third example I'm doing. This I will do balls into bins. Okay, always ends up being a little bit tricky, and we will not do it in great detail. But anyway, so I think it's good to finish up with slightly more complicated. Let's take 5 balls into 3 bins. Okay, so you have 3 bins, 1, 2, 3, and you're throwing 5 balls. I'm going to define 2 random variables here. So let's say x is similar to before, number of balls in bin 1. Y is number of balls in bin 2. Similar to before, nothing very fancy. And if you want to do x, y here, maybe I want to make this even simpler. So I'll just say 3 balls into 3 bins. Okay, I'll make it very, very simple so that we don't have to write down long calculations. Okay, so there are 3 balls. So the first bin could be 0 or 1 or 2 or 3. Likewise, the second bin could be 0 or 1 or. And we know that this, there is this. There are only 3 balls that were thrown, so you can't have too many balls beyond this. So some things will go to 0. So for instance, 3,1 will go to 0, 3,2 will go to 0, 3,3 will go to 0, 2,2 will be 0, this will be 0, this will be 0. So the upper triangular part, lower triangular part will go to 0. And some of these other things are easy to write down. For instance, 0, 0, all balls should go into the third bin, right? So that is just 1 by 3 power 3. Okay, so same thing will happen for this guy, right? 3 comma 0 means all the balls should go into the second bin, so that will also be 1 by 3 comma power 3, right? So some of these calculations are easy to do, right? All balls should go into the first bin, all balls should go into the second, no, all balls should go into the third bin. Okay, this is that probability here. So this one is all balls should go into the second bin, and this guy here on this side is all the balls should go into the first bin, right? So that's an easy calculation to do. All other calculations are a bit tricky. So let's try. You can try it. I'm not going to do this in great detail here. So all these calculations have to be done. There is a symmetry here, so you don't have to really calculate everything exhaustively. If you calculate the ones on the top right, you'll get the ones on the bottom also exactly to be the same. Symmetry is going to help you, but nevertheless you have to do a calculation here of at least 3 or 4 numbers. They are a bit messy, but if you do that, you will get a joint PMF, and with this joint PMF you can do a similar calculation there. So for instance, you might ask the question, what is the probability that x is greater than y or x is equal to y? Okay, so let's ask that question. So what's the probability that x will be greater than y? So on the face of it, it looks quite difficult to compute this, but one can say some interesting things about this situation. So for instance, so if you think about this, so even though we don't know much about what is probability of x greater than y, we can say for sure that these two will be the same, right? Probability that x greater than y and probability that x less than y will have to be the same. Why is that? There's symmetry in the situation, right? So whatever is on the top right side will be the same as what's in the bottom left. So if you look at x greater than y, y greater than x, those are those two events, right? So x greater than y is this event, x greater than y, and y greater than x is this event, right? So we can say that these two will be equal, okay, because of the symmetry of the situation. So this kind of reasoning is very interesting to do in many problems. So even though you don't know much about these probabilities, actually you can compute them. I'm not saying it's very hard, but still, without even computing, you know that these two will be true. In fact, you can even say something more. If you look at probability of x equals y, okay, right? This plus probability of x greater than y plus probability of x less than y have to be equal to 1, right? So that's everything. So what is x equal to y? It's this guy, right? This is x equals y. Okay, together they should all add up to 1. Okay, so these two are all the same, and these x greater than y and y greater than x less than y are also equal. Okay, so in fact, if you find the probability that x equals y, you can find the probability that x is greater than y and x is less than y without doing too much other work based on this symmetry. Okay, so this kind of reasoning will help your calculations a lot. Okay, so the only thing I need to really find to find probability that x greater than y is this guy. Okay, so what's the probability that x equals 1 comma y equals 1? Okay, so I have one ball in the first bin, one ball in the second bin, and what should happen to the third ball? It should go into the third bin. Okay, so what's the probability of that? So the first ball can go anywhere, right? It doesn't matter where it goes. The second ball should go only into the other two. Okay, so you have 2 out of 3, and the last ball should go only into the other 3. So you'll just have 6 by cancel, you simply get 2 by 9. So this probability is 2 by 9. Okay, so once I know that, I know probability of x equals y. So what's the probability that x is equal to y? Is 1 by 27, 1 by 3 power 3 plus 2 by 9. Okay, so that is 7 by 27. So what's the probability that x is greater than y? Okay, so if you look at this equation, these two are equal, and this is 7 by 27. So I should do 1 minus 7 by 27 divided by 2. Okay, 2 times this is 1 minus 7 by 27. Okay, probability that x is greater than y. So if you do this, you get 20 by 27, and divided by 2, you get 10 by 27. So that's the probability that x is greater than y. Okay. Okay, so I mean, of course, I can do all these calculations and come up with the answer. It's not very complicated in this case, but nevertheless, it's nice to reason like this. So supposing if I were to increase the number of balls to 5 balls, 10 balls, this kind of reasoning will still help you. I mean, it's not impossible to do. I mean, it's still hard, but not a little bit easier. So I'll stop with this as far as computations with joint PMF is concerned. This is quite important. Like I said, given a joint PMF in this simple form like this, you should be able to find the marginal, you should be able to find conditionals, and you should be able to find probabilities of